LeetCode Problem 1. To-sum. At first glance, it feels like a warm-up, but this one's got depth, real-world depth. Think of systems tracking paired events, financial apps matching transactions, or alert tools flagging offset conditions. The real test? Doing it fast. With arrays pushing 10,000 elements, brute force drowns. We need to stay afloat and swim towards something leaner. All right, ducklings, time to splash into our first attempt, brute force. It's not elegant, but it works. Let's walk through how it plays out in code. We kick things off with an outer loop that scans each number. This locks in the first half of our potential pair. Then, we nest an inner loop that scans everything after that number. This keeps us from checking duplicates or reusing the same index. With both indices picked, we check if their sum hits the target. If it does, boom, we've got our answer. Return those indices right away. If both loops finish with no match, we throw an exception. But don't worry, the problem guarantees exactly one solution, so this line should stay unused. Time complexity here is big O of n squared, up to 100 million operations on a 10,000 element array. Space is constant, big O of 1. Not bad for small inputs, but definitely not built for scale. So how do we cut the fat? What if we could remember what we've seen and skip repeat comparisons? Let's upgrade to a smarter strategy using a hash map. Step 1. Create a hash map to track each number alongside its index as we scan the array. This sets us up for lightning-fast lookups. We fill the map with all numbers and their indices. This defers the actual search. We're just prepping the data for a fast second pass. Once the map is ready, we scan the array again, this time looking for complements, numbers that pair with the current one to hit the target. For each number, we calculate its complement, the missing piece that would add up to our target. We check if that complement exists in the map and that it's not the same index. If it passes both, we return the indices immediately. This fallback line is just a safety net. With a guaranteed solution, it should never run, but it's here just in case. This method runs in big O of n time, 2 full scans. That's about 20,000 operations for 10,000 elements. Space complexity is also big O of n for the map. We're trading memory for serious speed. But can we go faster? Let's see if we can tighten this down to just one pass. To pull this off, we'll use a hash map while scanning, storing each number with its index as we go. This lets us check for matches in real time. Now we process the array in a single sweep. For each number we ask, can it pair with something we've already seen? At each step, we calculate the complement, what we still need to hit the target. Then we check if it's already in the map. If it is, that's our pair. Since we stored its index earlier, we can return both indices right away. If not, we stash the current number and its index into the map, so later values can match against it. This final line is just a formality. With one solution guaranteed, we shouldn't ever hit it, but it covers us for edge cases. Now we're at big O of n time and big O of n space, just one clean pass. That's as efficient as it gets. Perfect for interviews and solid in production systems where every millisecond matters. We started with brute force, simple but sluggish at big O of n squared. Then we leveled up with a double pass hash map for speed. But the real win came with our single pass approach, lean, fast and scalable. This is the kind of optimization that stands out in interviews and powers real-time systems. So here's your challenge. Where else can this pattern shine? Try it out, tweak it, and keep honing that algorithmic edge.